Hello YouTube, welcome back. Alright, let's take a look at Chapter 4, Section 5. We only did the evens in class, so let's focus on those. Alright, so, note to self, this is Computer Science Honors 405. Let's say even. What is iteration? Well, we've been doing this with for loops and list comprehensions, or shorthand for loops, but they want you to focus now on while loops. So let's see, what is iteration? Really, what is a while loop? And today is the 14th. And put your name over here in case you got to print. Whoops, why is the caps lock on? It's still on. There you go. All right, so let's show number 2. We're starting with 2. We're doing the evens. Okay, so can you print out a times table using a while loop? Okay, so print out a times table using a while loop. So what did we do? We actually wrote a function. We said define times table with 2 parameters. Num is the table we're talking about. So if num is 6, we're doing the 6 times table, like 6, 12, 18, 24. If num is 5, we're doing 5 times table, 5, 10, 15, 20. And nmax is the largest answer. So let's see. Let's see. It should be like answer max. How about that? So up to a maximum answer. So if answer max is 100, you could do a times table that goes up to an answer of 100 and that sort of thing. Okay. All right. So what did we do? We initialized n to 1. Okay, and n is the number of times we're printing out a row in the times table. We're going to make it a times table with, I guess, 2 columns. Can we do 2 columns out of this? All right. So let's think about that. Let's make 2 columns. So we're going to say, let's start with answer starts with num. So the first output is 6 if num is 6. Let's use a print statement. We're in Sage, we've upgraded to Python 3.0, so a print function, not a print statement, requires parentheses. So I'm going to print 2 headings, n, then tab, and then answer. How about that? All right, so this, when you invoke this function times table, it's going to do the whole table, including the heading. Okay. So here's the while loop. While, let's see, answer is less than or equal to answer max. So we'll allow 100 in a times table of 5, right? Colon, what? What are we going to do? Well, let's print out what we got so far. So print. Now be careful. In the print statement, you can only print strings. So how about we stringify? That's not English. Don't tell your English teacher. Then tab. Remember, tab is an escape sequence that has to be a string. So put it in quotes. And then let's stringify, again, that's not English, sorry, the answer we got so far. So the first output is going to be 1, 6, if num is 6, right? Okay. But then how do we generate the rest? Well, we have to increment num, and we have to increment answer. Boom. So every time we're going to add 6, we're going to add 6, we're going to add 6 if num is 6, right? So it'll be 6, 12, right? It's not the 12 times table. It's really a lot of adding. Okay, I think that's the whole thing. So this particular function is one without a return statement. So if I show what I get from invoking times table, of, I don't know, let's say 5, 100. Let's see what we get. Whoops, what did I do? Line 11. I didn't close the show. Nope, that's not it. What did I do? Why do we have 2 shows? What is that? That's crazy. I want this here. Why did I copy everything? That's weird. Now I messed up. I don't want that either. Okay. Oh, it's times table. What did I put? Times. I call it times, right? Times table. Say what you mean what to say. And what happened there? doesn't like line 11. What did I do? Oh, n, I have to say what n is. N is, let's say a 5 times table. And there you go. And it goes up to 100, see? So 5, 10, 15, 20, 25, 35, right? Now what if I change it to n is 6? Now be careful. This here, this is the show, and show and print don't play nice. So ignore this gap. So 6, 12, 18, blah, 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 up to a max of 100. Well, the next one would be 102, right? That's why it doesn't print 100 or 102. So that's a 6 times table. Yeah, okay. How about a, I don't know, an 11 times table? Where is it? Oh, I didn't change it. Here. So evaluate it. And 11, 22, 33, 40, yeah, up to, and including 100 if you get 100, but you don't, the next value would be, what, 110, and 121, and so forth. All right, so why is it printing none? Because there's no return statement. Alrighty, what if we said, what if we didn't, could we get away with print here? It still does the none, but it plays nice with the other print, so, okay, that's fine, I'll leave it as a print, that's fine. All right, so that's our output for number 2. So there's number 2's code, a function with a while statement in it, or while loop, and there's your output if you're plugging in an 11 times table and the output is less than 100. Okay. All right, nice. Next, all right, let's separate the output. And let's do number 4. Okay. So number 4 says, make a table with these headings. N, S1 of N, S2 of N, and what is 3 times S2 of N divided by S1 of N, where N could be, 1, 2, 3, 4, 5, whatever n wants to be. And S1 is the sum of the first n consecutive integers, and S2 is the sum of the first n squared, perfect squares, okay? And the question is, since we know a rule for this, n times n plus 1 over 2, where n is the number of terms, right? Can we now deduce a rule for the sum of the perfect squares? That's what we're going to get, because we're going to get a pattern out of this. That's the idea. All right, so here we go. So we're going to do a table again. Let's see. Let's think about this. Or do the same kind of thing. Let's define a function. Now, I don't know what it's going to do, so I'm going to call it mystery. And I'm going to say go up to a certain n max. All right, so if n max is 10, the first column goes from 1 to 10. If n max is 20, the first column goes from 1 to 20, right? Okay. And that's what I want to do. I want to just generate this table. Okay, let's make it easy. Let's start with n equals 1. Okay. Let's print out a header. Let's just do one column at a time. Let's do the n column. So I'm going to print out n as your header. And then while, now if we want to stop with n max, we're going to say while n is less than or equal to n max. Okay, what are you going to do? You're going to print the string version of n. Print the string version. Remember, you can only print strings, right? And n is an int, so let's make it a string. And, okay, that's it for one column. Let's see what mystery 10 does, for example. And again, this doesn't have a return statement. That's okay. When we talked about functions that don't have return statements, it's all right. So let's show what mystery of 10 does. So let's label this. And I should just have one column, 1 through 10. 1 through, whoa, what happened? Oh, I have an infinite loop. Why? Why? Be careful, we ran into this in class. What happens if, okay, you have 3 kinds of loops, okay? The loop that you want, this ain't it. The loop that never stops, an infinite loop, and the loop that never starts, or only iterates like once. And the problem is, I never, Sage is going nuts now. I never incremented n. So can I change the code here? Don't I have to increment n? Yes, I do. So let's do n plus equals 1 and reevaluate. Oh, there you go. So 1 to 10. And again, here's that mystery none, and it's centered because of the show. I could do a print instead, I guess, if I want. Right, I'm talking about this. What if I put a print here? You know, show and print don't mix too well, so how about we just do all prints? Okay, there you go. So there's the output of the first of question 2. There's the output of question 4. It's a little bit weird without the separating the show thing, but okay, that's fine. All right, so that's the first column. All right, let's get the second column. The second column is the S sub 1, the sum. So in other words, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, the triangle numbers, right? So let's do that. So now what I want to do is let's create sum 1 starting at 1. So it's 1 and 3 and 5, 1 and 3 and 6 and 10, right? Okay. And then let's add that with a escape sequence tab sum 1, right? Or yeah, that's fine. And then let's print that out too. So what are we going to do? We're going to say, just like we did with the print statement up here, concatenate with this escape sequence, and then let's stringify sum 1, right? All right, so let's do that. Concatenate, then a string escape sequence for tab, concatenate with the string version of sum 1. Remember, there's 2 sums going on, right? Alrighty, and don't forget to increment sum 1 with what? Well, we're adding up the ends. So there you go. And all right, let's see what we get now. So 1, 3, 6. Right, we're just adding this up. And 5 is 15, and 6 is 21, and 7 is 28. That's perfect. Nice. Okay, good. Now let's get sum 2. Now sum 2 is the same idea. Let's start it at 1 because the first one is 1 squared. We're doing the perfect squares, right? So let's add another heading. And again, let's add another column. But what is sum 2 summing? It's summing the perfect squares of n. All right, see how that works. So 1 squared is 1, plus 2 squared, plus 4 is 5, plus 9 is 14, plus 16 is 30. That's good. Okay, now I want to see what this works out to be. I got this, 1 to 10. I got this, 1 to 55. I got this, 1 to 385. Let's see what this works out to be. And you're going to see that there's an obvious pattern. Alrighty, so there's nothing else I have to initialize. There's nothing else I have to increment. I'm just going to print out the next thing. Plus, or concatenate, string /t, string, concatenate, the string version of this calculation. 3 times sum 2 divided by sum 1. Is that what it was? Yes. Alrighty, so let's see what we get for the fourth column. And I have to do a header. Alright, so those headings should line up. There you go. And, it's not what I wanted. What did I do? I did something different because we got a nice pattern. We got odd integers, like I think 3, 5, 7, like that, right? If you plug in 1 into 2n plus 1, you get 3. Plug in 2, you get 5. Yeah. Did I type that wrong? What did I do? Sum 2 over sum 1 3 times. And you get 3, 5, 7, 9. So we said, well, what's the rule for this? I know the rule for this. It's n times n plus 1 over 2, the sum of this arithmetic sequence given n terms, right? Okay. I don't know a rule for this, but I know a rule for this. If I plug, all right, so are these are all odd, right? So is n odd? No. Is 2n odd? No, it's 2, 4, 6, 8, it's even. What if you add 1 to that? 2, 4, 6, 8 plus 1, 3, 5, 7. Yes, this is 2n plus 1. All right, so this is what we figured out. This works out to 2n plus 1. This works out to n times n plus 1 over 2. So can we figure out what this is? All right, so we wrote it down as like a comment, okay? So here we go. Show. Number 4. Result. This is what happened. This is what we got. we got that 3 times S2 of n, or sum 2, divided by S1 of n, or sum 1, is equal to 2 times n plus 1, right? But we also know that sum 1 is the quantity n times the quantity n plus 1 over 2. So can we get a rule for S2 out of this? What would you do? Divide by 3, this thing divided by 3, and then multiply by this, right? So this is the result. This is what we got. We get that S2 is this divided by 3. So let's do that. This divided by 3 times this part, which was this. Whoops, I wrote it wrong. Which is, in fact, just quantity over 6, right? We're dividing by 3 and dividing by 2, so we're dividing by 6 at 6. And what's that quantity? It's n, let's write this out. It's n times n plus 1 times 2n plus 1. And that's it. All right, so the question is, can you make a table for this and then figure out a rule for this? And we did. There it is. Done. And boom. You know what? Let's make this 2 lines. Is that easier to read? All right, so this turns into the odd numbers, the consecutive odd numbers, starting at 3. Then you divide. Then this, we knew a rule for this already. So we want to get this alone, so we divided by 3. So this, here it is, divided by 3, here it is. And then multiply by this, and there's your rule. Ta-da! And so let's see if that's true. If I add 1 plus 4 is 5 plus 3 is 9, so if I add the first 3, I get 14. Let's see, plug in 3. 3 times 4 times 7 divided by 6. 3 times 4 is 12 divided by 6 is 2 times 7 is 14. Is that what we got? 14, yep, works. So 3 is the number of terms. You plug in 3, you get 14 is the sum of the first 3 consecutive even integers that are positive. You're good. Nice. All right. One more question I think we did. Number 6. Can you write a POW method, my POW method, that returns x to the n, and use a product loop? Don't use the caret or the star star. Okay, let's do that. Here we go. So let's put in a blank show here, and show number 4. Okay, so make a my POW method with a base of x and an exponent of n, returning x to the n using a product loop. Don't use carets, don't use star star, none of that stuff, okay? So this is what we did. Define my POW. Base is x, exponent is n. And so what we did was we initialized the count to 0. What is that? How many times we multiply, right? Because isn't like x 5 to the third just multiplying 3 times? 5 times 5 times 5. So we're going to keep track of how many times we counted. All right. And then we kept track of the power so far. Well, let's initialize. Now we can't initialize it to 0 like we usually do with the sum. Initialize it to 1, so we multiply by x, the base you get. Say x is 6, so 1 times 6 is 6, times 6 is 36, times 6 is 216, and so forth. So you get powers of 6 if x is 6, right? Okay. So while what? While the count, how many times the loop iterates or multiplies, is less than, it's less than n, the exponent, do what? Well, what are you going to do? You're going to increment count, and you're going to multiply the power by the base. Right? So if n is 3, you're going to multiply by x, you're going to multiply by x, you're going to multiply by x, you get x cubed, right? Okay, there you go. And then this one, we're going to actually return the answer, which is the power. So this is a return. This one has a return statement. And let's test it out. What is, say, 3 to the 4th? Let's see. Show, quote, comma, my POW of 3, 4. Well, that's 3 times 3 is 81, and 81 times 3 times 3 is 9, and 9 times 9 is 81, right? That's it. So we should get 81 out of this. Where'd it go? There it is. Perfect. Also, so that's a product loop rather than a summation loop. These are summation loops using while. This is a product loop using while. And it doesn't have to be ints. I mean, you could show my power of anything. How about, I don't know, something like 15.3 to the 160th. I mean, you could do anything you want. So how about 15.3 to the 160th power? Aha. We have the power to do this in our supercomputer. And now we get some huge scientifically notated number. That's fine. Okay, good. And that was not number 4, that was number 6. All right. So there you go. So this is the output for 4. This is the output for 2. This is the commentary for 4. This is the output for 6. Okay. Numbers 8. Okay, so that's it for the evens. Once we do 8. Number 8. Print out a table of perfect numbers. What's a perfect number? A perfect number is an integer that equals the sum of its factors or divisors that go evenly into it, except for itself, right? So, for example, 6 is a perfect number because 1 plus 2 plus 3 is 6, right? What are the factors of 6? 1 and 6, 2 and 3. Add up all the factors except for 6 itself, and you get 6. But the thing is, it's hard to find these numbers. So here's an example of a perfect number. So can we make a table of that? Okay, so what we did was we created a function called sum of divisors. And we plugged in whatever number we wanted, say number. It doesn't have to be x all the time or n all the time, right? And so what did we do? All right, we initialized my sum to 0, which is what we usually do with a summation loop. We're adding up all the divisors. We want to see if it adds up to 6 if we plug in 6, right? Let's start with the first divisor. Well, 1 goes in, so 1 works. So the first divisor is 1. And then what did we do? While the divisor is less than the number, because we don't want to add the number itself. The number itself is a factor, but it's not one of the factors we use to determine if it's a perfect number. So while divisor is less than number, what are you going to do? You're going to find out if the number goes in. So sorry. So if the divisor goes in. So if num or number mod divisor equals 0, Boolean equals, right? Then divisor went in, right? So we're going to want to add that up. So my sum plus equals that divisor. So the 1 will be added on, the 2 will be added on, the 3 will be added on if our number is 6, but not the 6. Okay. All right, there you go. And then don't forget to test the next divisor. We have to increment divisor. Otherwise, you get an infinite loop. If you don't change the value of divisor, that while statement will always, the line 49, the Boolean, they will always be true, and you'll have an infinite loop. You don't want that. So how about plus equals 1, and test if 2 works? Okay. Test 3 works? Okay. Test if 4 works? No. Test if 5 works? No. Don't test 6, and you're done. Okay. So when you're done, let's return what? The sum. All right, so what does that do for you? Well, then what we can do is print out all the perfect numbers. Perfect integers, really. That's a heading, okay? And then what we're going to do is, how about a for loop for a change? For I in range, let's start with, I don't know, 10. What are you going to do if the number equals the sum of its divisors, so I being 0 through 9 in this case, then print it out. Print that number I. All right, so let's see. Well, the first integer, what I do? Oh, there's no space here. What is that? All right, so if you start, well, 0 apparently is a perfect number if you're starting with 0. If you don't want to include 0, start 1, 10. That's good. And so for the integers from 0 through 9, there's only those two perfect numbers. All right, let's try from 0 to 100. You know what? I don't want to include 0. So how about let's include 0. Let's go to 100. All right, so how many perfect numbers, perfect integers can you list from 0 to 99? 0, 6, and 28. Okay. How about from 0 to 999? 0, 6, 28, and 496. They get very far apart. It's really hard to predict ahead of time. So using a function like this and a loop like this is really the way to go. All right, so those are the perfect numbers. Think about this. Yeah, that's all I'm going to print because this is only one column because it's not like n and it's I and I, right? So that's sort of silly. All right. So, okay, let's go up to 9,999. So they can get any more. How about 99,999. Oh, I see. It's stuck in a loop. It's taking too long. Okay. So let's just do 100. So from 0 to 100, it's only these three values. Okay, we're done. That's it. All right, so there's your code for number 2. That's it. There's your code for number 4. Well, there's a result for number 4. There's a code for number 4. There's a code for 6. A little snippet of Pythonic code or a Sagelet, if you like. There's your code for 8. Well, there's the function. And then there's a for loop to print out everything. All right, there's your output for 2. Yeah, they got messed up there. There's your output for 4, and that's the result of it. There's your output for 6. And there's your output for 8. And you're done. All right, good. Hope that was helpful. Bye-bye, YouTube. Have a nice day. Good luck with your lab. We're doing a lab now, lab 4, based on this. Okay, bye-bye.